Hello everyone, today we're going to solve a heat transfer example. As you can see, the air is flowing through a duct with a structure that you can see in this figure. The air is coming from the inlet and goes out from the outlet and passes over a solid wood domain in which the wall down, you can see the wall down, has a constant temperature of 600 Kelvin, and the other walls are insulated or the heat flux are zero. Okay, so we're going to solve we're going to solve and model this domain and see the results, the asked requested results, and have some discussions. Okay, in part A we have two parts. In part A we have velocity of air is 0.1 meter per second. So let's start simulating the part A of this problem. Here, if you remember that to model a problem, we opened Workbench, we started by creating the geometry and then generating the mesh, and after that set up the fluent with the boundary conditions and operating conditions, and after initialization and running the model, we had results and some discussions about those results. Okay, but here you can just simply download the uploaded mesh file, which the name is tb.msh. Okay, and just simply download this .msh file. But if you remember that when we wanted to go Fluent and open it directly from a start bar, the problem was that in that case we didn't have access to our desktop. So in that case, it's better to save your mesh file on your folder name, which is under ECF users and your folder name. Okay, now open Fluent directly. Here, just remember that we always have to check double precision. We can check the display mesh after reading because we wanted to see our mesh after reading it. This dimension is really important here because the domain or the geometry is 2D. So we keep it as 2D, but make sure that you change it if it's needed. Okay, now we're going to read the mesh file. That's our mesh file. Something important here, if you can see that this one, which has the let's say uniform or the same size of the cell sizes, is the fluid domain. It's this solid domain, and this one is the fluid domain. If you remember, then whenever a fluid just passes over a wall or near the walls, close to the walls, a boundary layer will be formed. And to capture the gradient of the flow properties close to the walls, we need to have finer mesh adjacent the wall. So here you can see the finer meshes close to the walls. Okay. So the first thing after reading the mesh is checking the mesh. If you remember, the important criteria was that the minimum volume should not be negative, which is not here. The other one that I just wanted to show you is display. Here, if you go through the outline, deselect everything, you can see if I just select inlet, you can see the blue line shows the inlet influent. If I go through the selecting outlet, it's gonna display by a red line. If I go through the other options, which are walls or other options, are gray. Let's say this is wall down, wall left, wall right, wall up, and of course part surface body, which is a line between two different zones. So the part surface body is the line that's, for example, we just created in our geometry with that name. But you can see another option which is called that, which is with the same name and a shadow name. So what does that means? Whenever you have an edge or a boundary between two different cell zones, Fluent automatically create another the same a line. For example, it's consider that line for one zone, one of the zones, and it just created another line at the same location with the same name but with shadow for the other zone. So here it's just created by Fluent. It's the same. In interiors, if you remember that interiors are created by Fluent as well. Okay, let's go through model. In models, we need to activate our energy equation since we have heat transfer. How about the flow? We have to calculate the Reynolds number to make sure if it's flow laminar or turbulent. So let's go here. In part A, the velocity is 0.1 meter per second, and let's put the rho, which is the density, and dynamic viscosity from here. So it's 1.2. This one is 1.2. Okay, so what is area of the inlet? The area of the inlet is 10 centimeter, which is 0.1 meter, and the width, which is perpendicular to the page, is 1 meter. So it's going to be equals to 1 point multiplied by 1. And the wetted perimeter, it's going to be 2 times 1 plus 0.1. If you remember, hydraulic diameter is 4 times of area over wetted perimeter. So this is our hydraulic diameter. And if you remember, the Reynolds number is density multiplied by velocity multiplied by hydraulic diameter over dynamic viscosity. So it's less than 2000, so it's going to be laminar. Okay, so in the first part, we don't need to change laminar to turbulent. Okay, closed models, go to materials. The materials is air, but we have to change the necessary properties. Okay, let's go back here, double click on air, change density and viscosity. Okay, go back to the problem. The solid is made from wood, so we have to add solid major types, solid and wood. Copy, close, and we have wood and aluminum. At the end, because I don't want to have a mistake, and I just suggest you that I wanted to delete the unnecessary materials here in this problem. We don't need aluminum, so I just wanted to delete it after changing everything to wood. Okay, close materials, open cell zones. Of course, we have two zones, fluid domain and solid domain. By clicking on fluid domain, make sure the type is fluid. and by opening it, make sure the material and name is air. We don't have any other fluid materials here, but it might be in other problems. Just make sure that the material is correct. By clicking on solid, you can see the type should be solid, and it's in aluminum, so the material should be changed to wood. Okay, by going to boundary condition, the inlet velocity magnitude normal to boundary, and it's 0.1. The thermal condition, the default is 300, and we don't need to change it because it didn't mention through the problem. The other one is pressure outlet. Again, we don't need to change the default of the temperature for the outlet. Just simply close it, bolt down, open it. Okay, from the problem, bolt down is the constant temperature goes to 600. Okay, so we have to change it to 600. The material should be changed to wood. Wall left, it is insulated or heat flux is 0, so we don't need to change anything. And the material doesn't matter here, but I just, because I want to delete aluminum to make sure that everything is correct in our setup, so just change it to wood. The same for thermal condition, insulated for wall right, okay, and the same for wall up. Okay, we know that the interiors again are the something that are created by fluent inside the zones, fluid zone and solid zone, and for part surface body, which is this line between these two zones, the type is raw, but make sure that the thermal are the same. Here, because we don't have any heat flux temperature, but it's coupled means that the heat can transfer from solid zone to the, from here, this zone, solid zone to the fluid zone. Okay, change it to wood. Make sure we have the same condition that we have in the shadow one. Now the boundary condition is completed. Go to methods, change scheme to simple, change gradient to green Gauss cell base, change pressure to standard. Go to monitors, change continuity, x and y velocity to 1e-4, and keep it as 1e-6 for energy. Now we need to initialize the domain. So can start from inlet. As you can see here, we entered 0.1 normal to the boundary, which was in the x direction, but we have a very small near close to 0 in y velocity, and the reason is that, for example, we might had a mistake in geometry creation, and the inlet was not exactly vertical. So we can just change it to 0, initialize. After initialization, you can simply write your case and data. And let's say that we wanted to change it to part A, which is laminar. Okay, now save. Run calculation, start with something, calculate. So the calculation is completed after 140 iterations. Now we're going to graphics contours, see we wanted to see the velocity, and we can, if you remember that I explained, we can see our domain by clicking on draw mesh and outline our domain here. Okay, and then click on velocity, and you can see that's the velocity magnitude over the domain. Okay, of course the velocity close to walls are 0, and you can see the boundary layers creation performed near close to the wall. Okay, and then we wanted to see the temperature. So again, you can see how the temperature is transferred from the solid zone to the fluid zone. Okay, and also we can color it by bounded, so you can see the bounded contours of temperature, velocity. Let's go to plot, XY plot, and let's plot velocity at the outlet. Of course, it should be in Y direction. Okay, so this is the velocity magnitude. If I wanted also to show the inlet velocity, which was uniform velocity, you can see both inlet and outlet velocity profile at the outlet. Okay, over the inlet and outlet. And the temperature, of course, the temperature at the inlet was 300, and you can see how the temperature changes from at the outlet. There are two important variables or values that we can conclude it or calculate it here. The first one is go through the surface integral mass weighted average. We wanted to see and calculate the mass weighted average of temperature at the outlet. Okay, I am gonna save this one because at the end we wanted to discuss about our results. Also, by going to fluxes, if you wanted to make sure that your calculation and your model works perfectly and it's correct, so you can go to mass flow rate and click on both inlet and outlet, and you know that the net difference should be very small and close to 0, which is here because of the conservation equation, okay, or mass conservation equation. Okay, and then we wanted to see calculate the total heat transfer from the solid zone to the fluid zone over the surface body. Okay, also need this value, so I'm gonna keep it here. Now that we have the results, we're gonna save it again with the same name. Also, we wanted to save it as for the turbulent part, so let's change it to turbulent and part B. Why part B is turbulence? Let's go back here, and the velocity of the air is in part B is 1 meter per second. So going here, let's say it's part B, and the velocity is 1. Up to here, you can just drag it, and you can see the Reynolds number is much higher than 2000, so it's going to be turbulent. Okay, So in part B that we just saved it as part B turbulent, we're going back and change the viscous to turbulent, laminar to turbulent. And this course, we're gonna only use K epsilon model. We don't change any models, constants, anything here, near wall treatment. And if you wanted to get more familiar with K epsilon and the other turbulence model, you have to go to help or Google it. And based on your future problem, you can get or can you choose one of these models. Okay, materials, we don't need to change anything. In boundary condition, of course, we need to change the inlet. Okay, just forgot to have to select this one. Okay. And after, you can see after activating the turbulence model, there is a specification method here. First of all, we need to change the velocity magnitude to 1. And we're going to use, you can see there are 4 options, but we're going to use the last one. We change the turbulent intensity to 10. And we're going to use our hydraulic diameter that we just calculated here. For the outlet, we do have the same turbulence, so we have to go to intensity and hydraulic diameter, change it to 10, and change it to hydraulic diameter as we calculated. So now the boundary conditions are correct. Let's go to the initialization again. We also can continue from, we could also continue running the model from the laminar, but I just initialize the model to show you that there are 2 other options that appears here after choosing the turbulent model, which is turbulent kinetic energy, turbulent dissipation energy. Initialize. We can save it again, the same name, and just go to from calculation. Okay, calculation is completed at 139, almost the same as laminar flow. We're going to see the results, contours, temperature. Okay, that's the temperature shows how it's changed from laminar to turbulent flow. Going to velocity, again you see how it's changed from the laminar to turbulent. You can just save these images and compare besides each other, the laminar and turbulent results. But we're going to the XY plot. Again, we wanted to see so you can see how it changes from the for the outlet temperature. So you can see that the outlet temperature is less than laminar flow in turbulent flow compared to laminar flow. We're going to talk about it more. So velocity profile here as well. And we're going to see the surface integral, mass weighted average temperature at outlet, and the temperature is going to copy here for the turbulent flow. going to fluxes, see the inlet and outlet mass flow rate, and you can see it's almost the same, which is correct. It shows that our model is correct. Then we wanted to see the total heat transfer over part surface body. Okay, so you can see that in the case of the turbulent flow, although the total heat transfer is higher than, you can see that we have a total heat transfer rate, higher heat transfer rate in the turbulent or in part B compared to laminar flow in part A. And the reason, of course, from the heat and mass transfer courses, if you remember, that since the Nusselt number is related to Reynolds number, and Reynolds number in turbulent flow is higher, so we're going to have a higher heat transfer from the solid zone to the fluid zone in the case of turbulent flow. But you can see also we have less outlet temperature in the turbulence flow compared to the laminar flow, and the reason is because we have a higher velocity inlet, so we're going to have a higher mass flow rate, and it's causes a less outlet temperature for the turbulent flows compared to laminar flows. And so based on this, considering this fact that in the case of turbulent flow, although we have higher higher transfer from solid to fluid zone, but still we have less temperature outlet. So this option shows that the turbulent flow is more favorable for heat removal from some surfaces. If we wanted to have we wanted to remove amount of heat from a surface, so the turbulent is more efficient that way because it takes higher heat transfer from the solid, but at the end the outlet temperature is also less. Okay, so we're going to just save this one, just save the final results in turbulent. And that's it for this problem. And thank you for your attention.